Hello, everybody. Today's discussion starts talking about hypothesis testing. In last week's unit, we were talking about confidence intervals, constructing that interval that gives us an estimate for the population parameter based on that sample statistic. Today, we're going to look at hypothesis testing, which is using that information now to use that sample statistic to make a conclusion about a population parameter. So we're going to be covering the first three sections here, just basic hypothesis testing and then tests on proportions and means. Our key concept is we're looking at, first of all, in this section, just presenting the steps in a hypothesis test and how to formulate those hypotheses. And then we'll go on to look at basic tests. We will only be doing tests for proportions and means. We're not going to be looking at standard deviation and variance in this class. So the first step is to look at the hypotheses. The hypotheses, there's going to be two of them in every test, and they are statements about making a claim about the population parameters. And they need to be worded in such a way that one of the two has to be true. The two hypotheses have to be complements. In other words, if one is true, the other one can't be, or if one is not true, the other one has to be. And so then the hypothesis test is just a procedure for going about testing to see which claim is more valid. We'll either look at refuting a claim or finding evidence, not necessarily in favor. We're really looking to gather evidence against a claim so then we can move on to its alternative. So one of the examples we use in this textbook is talking about internet users using two-factor authentication for their online accounts. And so the claim here is that more than half or a majority of people use two-factor authentication. Now the first key in any of these is to take a claim like that, where it says a majority use two-factor authentication, and put it into mathematical symbols. And so this is talking about a proportion. We're saying more than 50% or more than half. And so that would be the P, the proportion, is greater than 0.5. So now as we look at the possibilities here, first we have the big picture. We have that claim out there that the proportion is bigger than 50% or greater than 0.5. We have access to data for 926 consumers. We are going to assume that that is a randomly selected simple random sample. We need that for this data, or for this process. Now, what if we're looking at testing to see if we can affirm this claim that a majority or more than 50% use two-factor authentication. And there are three possibilities here. The first two, we don't really need to test much for. Clearly significantly high means, or not significantly high, I should say, means it's not big enough to say that there's any significance to it. In other words, here we're saying it's greater than 50%. Well, what if we get a result that's like 51%? So that's going to be too close to tell. So if we get like 464, which is 50.1% out of the 928, that's just barely more than half. That is not, it's clearly not significantly high. It's way too close to the center to tell. Then we have the option of being definitely, clearly significantly high. So if we had 925 out of the 926 that did use two-factor authentication, that's 99.9%, we would then be able to say, oh, that's definitely, that's high enough that we can definitely say that it's true that more than a majority of people use two-factor authentication. Most of our results, though, fall in this third category where it's unclear. Let's say we had 510 out of the 926, which is just over 55%. Well, we now can't say whether that's significant or not. It's kind of in the middle. And that's where the hypothesis testing process comes in, is ways of quantifying just how far where that's at on that spectrum of significantly high or not significantly high. So we're going to use technology where we can. Again, if you have Excel, I don't have administrator rights to my Excel account on my computer, so I can't load ExcelStat, but ExcelStat is an add-in you can add, and the textbook does go through using that. I will very quickly show you how to use the calculator, and MyMathLab has StatCrunch built right into it, so you don't have to use any external software. So for this test, we would be looking at claiming that, I'm going to expand this a little bit so it's easier to see, making the claim then that a majority or more than 50% use two-factor authentication. Now what we have here is different displays for different items. Let's start out with the TI-84. So this gives us z equals negative 1.25, basically, if we round that. That is called the test statistic. Below that, we have p equals 0.106. That's called the p-value. Now, don't confuse that with the p-hat here. That's the actual proportion of the data that in the sample that use two-factor authentication. These two values, the test statistic and p-value, are the two values we can use to draw a conclusion here. We don't necessarily, there's two different ways to set up the test. One involves using the test statistic and the other would be the p-value. Now StatCrunch is provided with MyMathLab, and you can see we have the test statistic there and the p-value, same values we had over here, just set up a little differently. We also, in StatCrunch, if you want to, we can get it to give you the critical value, which is actually very helpful. And then ExcelStat will give you similar information, test statistic and p-value. It does also give you the critical value, which we're going to get in StatCrunch as well. So shrink that back down, and we'll continue on here. So back to our example here. Most internet users using the two-factor authentication. So in our screens we saw up above, all of them had a test stat of about 1.25 and a p-value of about 0.106. So we're not necessarily, we'll show you how to calculate each of those, but we really want to focus on interpreting those numbers and what they mean. And what we're looking for is significance. So it's called a hypothesis test, but it is sometimes also referred to as a test of significance. So what we're looking at is looking at our data. Do we get a result compared on what we're looking for? Do we get a result that's significantly low enough to draw a conclusion, or a result that's significantly high enough to draw a conclusion? Again, based on how we formulate our hypotheses and then the data that we analyze. So the null hypothesis. The null hypothesis is really the hypothesis we're testing. It has the equal to portion of the inequality in it. And when we're doing a hypothesis test, it's important to note that the null hypothesis is assumed to be true. So we assume that null hypothesis is true, then we gather data and we analyze the data based on that assumption that the null hypothesis is true. And if we get a result that is significantly high or significantly low, then we go back and reevaluate that assumption of the hypothesis being true. The alternative hypothesis then is the one that is either just less than, just equal to, or not equal to. It must be true if the null hypothesis is false. So the two of them encompass every possibility. So our procedures, I'm going to blow this up a little bit. So you identify what the claim is that you want to make, and you put it in that symbolic form, like we did p greater than 0.5. So once it's in that symbolic form, we look at trying to decide then where we want to put it in our hypothesis. If that symbolic form includes the equal to, it's going to become the null hypothesis, H0. That little 0 is actually a naught. It's called H naught. If it does not have the or equal to, that symbolic phrase becomes the alternative hypothesis. We do have to select a level of significance. We talked about that 5% or 0.05 is the most common one, but we do sometimes use a 0.01 or even sometimes a 0.10 or other numbers in between there, depending on how critical our test is. We'll talk about errors later on in this presentation, which will help you understand what those numbers mean of the 0.05, 0.10. They're actually called alpha values. Like a 95% level of significance gives an alpha of 0.05. Then we identify the test statistic. Whether we're going to do a z-test or a t-test, we're not going to do chi-squared tests in here. Now, normal would be z. This textbook refers to it as a normal test, normal distribution. We're not going to do chi-squared in here. Those are tests for standard deviation and variance. So then we find the values from our sample. We find the values that we're going to look at. And then depending on what method we're going to use, if we're going to use a p-value method, we ask what is the probability of getting a test statistic that is more extreme than this one, and then we compare that probability to our value of alpha. If the p-value is less than or equal to alpha, we reject the null hypothesis. If the p-value is greater than alpha, we fail to reject it. Notice I didn't say we accept the null hypothesis. That's huge. We never accept the null hypothesis. We either reject it or fail to reject it. If we're using a critical value method, then we find that test statistic and we just compare it to the critical value and see if it's in the critical region of the bell curve or not. And then once we've done the test, we restate the conclusion in non-technical terms so that it can be understood in terms of the original question being asked. So we could also use, confidence intervals for doing hypothesis tests. It depends on the type of test being done. We'd have to convert our level of significance to get the appropriate confidence level for our confidence interval. And we will look at that as when we get into examples. A two-tailed test just means that the null hypothesis is that the value is equal to some number. So then the alternative hypothesis would be that the value is not equal to some number. That not equal to means we reject if we're too small or too large. So we're rejecting on two tails is what that means. If it's a two-tailed hypothesis, then we have to adjust the confidence level. If it is a one-tailed hypothesis, so that's where the alternative hypothesis is either strictly less than a number or strictly greater than a number, then we're only rejecting on one tail or the other. And so then we really have to adjust our level of confidence to go from one-tailed to a two-tailed confidence interval. All confidence intervals are two-tailed, by the way. So notice this level of confidence for the test or significance for the test corresponds to the percent for the two-tailed test. It's double this amount for the one-tailed test. So now we have 3 steps. We actually have 8 steps, but we're going to look at the first 3 steps for our hypothesis test. The first is to identify the claim to be tested. That's what and put it in symbolic form like we saw. The proportion is greater than 0.5. And then we look at that symbolic form and look at what must be true if that claim is false. So we get the complement of that symbolic form. Then we consider those 2 expressions and we decide which one is going to be the alternative and which one's going to be the null hypothesis. Remember, the null hypothesis is the one that has the equals sign in it, or the equals portion in it. The alternative is either strictly less than, strictly greater than, or not equal to. So back to this example for two-factor authentication. We have that claim. Step 1, we may put our claim in symbolic form. The proportion, or P, is greater than 0.5. The complement of that then would be that the proportion is less than or equal to 0.5. Well, this one contains the equal to, so that's going to be the null hypothesis. This one is strictly greater than, so that is the alternative hypothesis. And that was step 3, then, is determine which is which. So we have the null hypothesis is the one that has equals. The alternative is greater than. Now notice, when we wrote the null hypothesis, instead of greater than or equal to, we just put in the equal sign there. That's because we need that. We use it as equal so that we can create a hypothetical sampling distribution, and that's what we use to analyze our data. Step 4 then would be to select a level of significance. So for this test, it's nothing critical. It's not like we're testing medications or anything like that. What alpha is, that level of significance alpha, is the probability of rejecting the null hypothesis even though it's true. So it's kind of like a risk tolerance of, if we don't care, if it's vital that we keep this null hypothesis unless we're absolutely sure that it's wrong, then we would set alpha to be a really small number. So it's a very, very small chance of rejecting that null hypothesis unless it really is false. So in this case, we can choose any of those, 0.05, 0.01, 0.10. 0.05 is the most common, so that's what we're going to choose for this test. Number 5, identify the test statistic. Well, this is for proportion, so it's always going to be a normal distribution. So we're going to use a z-statistic for this test. And this table here illustrates what statistic, what distribution is used for each type of test. Again, we're not doing standard deviation and variance, so we're not going to worry about that. A little bit more complex formula for that test statistic anyway. For our proportions or means, our test statistic, first of all, for proportion, we always use a z with normal distribution. For means, we can use the z or normal distribution if we know the sigma. Sigma, remember, is the population standard deviation. So if we know the population standard deviation, we can use the normal distribution or a z statistic for the means as well. Normally, we do not know the population standard deviation, so we'd use a t statistic. T, remember, is a probability distribution like the normal distribution. It's always bell-shaped, but its width depends on the size of the sample. And then now this one here probably looks the most familiar. Our test statistic is basically calculating a z-score. It's our sample mean or sample data value minus the mean that we proposed in our null hypothesis divided by the standard error in our sampling distribution. So it's basically the value minus the mean divided by a standard deviation, just like a z-score. For the proportion, it looks a little different because the standard error is found by doing the square root of p times q over n, but it's really the same concept, same calculation pretty much. So for our two-factor identification, the claim that the proportion is greater than 0.5 is our alternative hypothesis. We have N is 926. We surveyed 926 people. If P is 0.05, Q is also 0.05. Remember, Q is 1 minus P. And so we need to test our requirements here. Remember, one of the requirements is that N times P has to be at least 5. In other words, we expect at least 5 successes. That's true here. And N times Q must be at least 5. In other words, we expect at least 5 failures, which is also true in this case. So then we find the value of the test statistic, and then either the p-value or critical values. Test statistic, this is a z-test. So for this example, since the z-test for proportions, we got a sample proportion of 0.52 minus our null hypothesis was p equals 0.5. So that's why we had to do the equal. So that goes in here as our mean, or in this case, our proportion. So we'd subtract those to get obviously 0.02. On bottom, it's the square root of p times q over n, so 0.5 times 0.5 over 926. We divide that out, we get 1.22 as our test statistic, which is pretty much what we had up above from technology. Technology gave us 1.248 or 1.25. This is just because of the rounding. The 0.52 is rounded as the sample proportion, and some of our other numbers are rounded as we go through our calculations as well here. If we wanted to do a test statistic, a critical value approach, we have to define the critical region. And that critical region is defined off of the alternative hypothesis. So if the alternative hypothesis, H1, I'm just going to use a proportion here. Say the proportion is not equal to 0.5. We'll use 0.5 because that's the number in our test here. That means if we get a sample value that's either too small or too large, we would reject our null hypothesis. So we're literally rejecting on both tails. That's why it's called two-tail. So our alpha is split to each side. So it's alpha over 2 on each end of the distribution, on each end of the bell curve. Kind of just like, or exactly just like what we did in our confidence intervals. Now, a left-tailed test, that would be if the alternative hypothesis is less than. So let's say the proportion is less than 0.5. The less than side is the left tail. So all of alpha goes on that left tail. And if we get a test statistic in that area, then we're in the critical region or the rejection region. And we would reject our null hypothesis. Right-tailed test then is if that alternative hypothesis is greater than. So let's say P is greater than 0.5. The greater than end of the curve is over here on the right. So if we had a test statistic that was in that area, we would reject again. The p-value method is taking that test statistic and looking at the alternative hypothesis and then using the alternative hypothesis to determine the probability of getting a test statistic that is at least as extreme as the one that we got. So in our two-factor authentication, the alternative hypothesis is greater than 0.5. So we want to determine with the data given here, with the information given, we have a test statistic of z equals 1.22 or 1.25 if you use the technology. We want to find what is the probability of getting a z-score greater than 1.25. And that's where that probability came from of the 0.106. So finding p-values, we look at what type of test. If it's a left-tailed test, we're finding the area to the left of the test statistic or the probability of being less than our test statistic. If it's a right-tailed test, then we're looking at the area to the right of our test statistic or the probability of being greater than our test statistic. If it is a two-tailed test, then it depends on which side of zero our test statistic is. If our test statistic is negative, we find the probability of being less than that value, and then we multiply it times 2. It's twice that probability. If our test statistic is positive, that means it's on the right side of the mean or of the null hypothesis. So we find the probability of being greater than the test statistic, and we double that. So don't confuse the following notations. P-value is that probability of getting a test statistic more extreme than the one we got from our data. P is simply the population proportion, and P hat is the sample proportion. On the calculator, you get P and P hat. Well, the P that's given on the calculator is actually a p-value, not a proportion. So make sure you know when you're seeing that notation for P, make sure you know what it represents, because different technologies use those symbols a little differently, and they're very easy to get confused between them. So the critical value method, like we said, we find that critical region and where the cutoff is, and then when our test statistic is either in the critical region or it's not. If it's in the critical region, we would reject. So here, if we're using alpha of 0.05, we look at this as being 0.05 probability. Well, we do an inverse normal to get the z-score for this cutoff, and that happens to be 1.645. Technically, remember, inverse normal uses the area to the left, so we'd be doing the inverse normal of a 0.95 to get that z-score of 1.645. So then we may make the decision to either reject or fail to reject the null hypothesis, whether we're using a p-value or if we're using a critical region. For p-value, if the p-value is less than alpha, we reject the null hypothesis. If the p less than or equal to alpha, I should say. If the p-value is greater than alpha, then we fail to reject. So in our example with the two-factor authentication, we have a p-value of 0.106. That is not less than alpha of 0.05. So since the p-value is greater than alpha, we fail to reject the null hypothesis. So there is not enough evidence here to conclude that a majority of people use two-factor authentication. So in this case, if we use the critical value, we need to find the critical region. We found that saying the critical region was, the cutoff was 1.645. This is greater than that. So if we get a test statistic of z greater than or equal to 1.645, we would reject. Well, we had a test statistic of z equals 1.25. That is not over in that region. It's actually here in the non-critical region, which means, again, we fail to reject the null hypothesis. Finally, then, we restate our decision in non-technical terms. In other words, we get rid of the whole idea of null hypothesis and test statistic, and we just state what the original problem was asking us. So in this case, we would state there is not sufficient evidence to support the claim that most internet users use two-factor authentication. We were trying to show that they use two-factor authentication. We needed to reject the null hypothesis in order to show that. We failed to reject the null hypothesis so that we do not have sufficient evidence to support that. So restating the decision using simple terms can be very tricky. Notice that we very seldom say support, especially the null hypothesis. We never say that we support the null hypothesis or accept the null hypothesis. The null hypothesis is either rejected or we failed to reject it. We're not trying to gather evidence in favor of the null hypothesis. We're trying to gather evidence against it. And either we succeeded and we rejected it, which means then we can support the alternative, or we failed to get that evidence and we failed to reject it, so then we can't conclude that null hypothesis is wrong in that point. So when we restate this decision, this is a little flow chart that just goes over what we just said again. I'll let you go back through. I'll blow it up a little bit so you can see it better if you're going through the recording. It just kind of goes through that process of restating it in simpler terms or non-technical terms so that the average viewer can understand what that conclusion really means. So the word accept, again, I stress this again, that can be very misleading. Do not say ever that you accept the null hypothesis. You failed to reject the null hypothesis. That does not mean we accept it. Don't ever say we accepted it. Multiple negatives. Sometimes, the way our hypotheses are worded can be, we do not have this. Well, we do not have enough evidence to show that we do not have this. It's okay to go through and change the wording when we're doing that non-technical conclusion statement. It's okay to go through and change the wording to take out those double negatives so it's not as confusing to read. Confidence intervals, as we said, can also be used for hypothesis testing. We saw that when we did our confidence intervals, there was some issues with proportions. Remember in the walled confidence interval for proportions, the percentage, the value of the confidence level, if it was a 95% confidence interval, that didn't necessarily mean that it was correct 95% of the time. It was slightly off. And there's a walled +4 procedure that's closer to being exact. But for the mean, it is exactly that percentage. And for the portion, it's close enough. It's really close to being 95% of those intervals that are correct. So we'll go ahead and use it anyway, even though it's not precise for proportions. Let's talk a little bit about errors in our testing. So it is possible to make an error, and the most most simple error to evaluate is a type 1 error. So a type 1 error is when the null hypothesis is true. HO is true, but we end up rejecting it. And remember, we said this probability was alpha. So if we're doing a 0.05 level of significance, that means there's a 5% chance that we will reject the null hypothesis even though it's true. So that percentage is easy to figure out. A type 2 error then is more common, even though it's more difficult to evaluate, because the test is stacked in favor of the null hypothesis, and because we assume the null hypothesis is true and we only reject it if we have strong evidence against it, there's a high chance of a type 2 error. The type 2 error is the probability of failing to reject the null hypothesis when it really is false. So this table shows us the types of errors. A type 1 error means the null hypothesis was true, but we accidentally rejected it anyway. It only can occur, a type 1 error can only occur when we reject the null hypothesis. If we fail to reject the null hypothesis, the only type of error that can occur, that could have occurred, is a type 2 error. Again, finding out what those chances are very difficult to do. There's something called beta, which is the probability of a type 2 error, but calculating beta requires that we know what the actual value of our test statistic or our parameter is, and we don't ever know what that really is, or we wouldn't be testing it. So if we're going to describe them, just look at that table and see the conclusion, knowing that if you rejected the null hypothesis, the only type of error that could occur is a type 1, and if you failed to reject, the only type is a type 2. And just going through describing that then for our situation, we failed to reject the null hypothesis, which meant that the only possibility is that we committed a type 2 error. But we're not sure. We could be correct. We could the null hypothesis could be true, and then in which case there was no error at all. So a type 1 error would be rejecting the null hypothesis, even though it really was true. There really is not a majority of people using the type 2 authentication. Now this example, they're talking about a medical procedure. So in this case, a type 1 error would conclude the medical procedure is effective when it really is not, which could be dangerous. Type 2 error would be assuming the medical procedure is not effective when it really is. So we failed to reject the null hypothesis, even though it wasn't true. There really is an effective procedure. Then the rest of these slides go into the power of hypothesis testing, which is calculating that beta. And like I said, it requires us to assume a value for the actual population parameter and go from there. We're not going to get into that in this course. So at this point, that's as far as we're going to go with this section of the textbook.